Hello, today we're continuing in our A-Level Physics revision series looking at the subject of circular motion. An object may travel in a circle. For example, if you attach it to a piece of string, you have a ball attached to a piece of string and you swing it round, it will travel in a circle. Or it may travel in a circle in the way that the Earth goes round the Sun. Strictly, this is the Sun, this is the Earth. Strictly, the Earth does not go round in a pure circle. It's a kind of ellipse, but it's near circular. And for these purposes, we will treat it as circular. And there's no string connecting the Earth to the Sun. The reason that the Earth goes around the Sun is that there is a gravitational force between the Earth and the Sun that causes the Earth to go around the Sun. And we'll see why a little bit later on. When an object goes round in a circle, even though its speed, v, may be unchanging, constant speed as it goes around the circle, it is nonetheless accelerating. The reason is that Newton's first law says that an object continues in its state of rest or uniform motion unless acted on by an external force. So if this body were to be free in space, then of course it would just continue to travel in the direction that it happens to be travelling tangentially. In other words, if this ball is going round on the end of a string, and when it got to this point here, you were to cut the string, the ball wouldn't continue going round in a circle, it would fly off at a tangent with velocity v. So that's its natural desire, but in fact, because you've got it on a string, it will actually travel down to here. So it will have been pulled in that direction, and that amounts to an acceleration. And in fact, the acceleration is always towards the centre of the circle, and it's called centripetal acceleration. And if you have an acceleration, then because of Newton's second law, which tells us that force is mass times acceleration, then the centripetal force will be the mass of the ball multiplied by the centripetal acceleration. And we'll work out what that acceleration is later. Now, it's relatively easy to calculate the speed or the orbital speed of the object as it goes round in a circle. Let's say that the speed is v, and let's say that the radius of the circle is r. What is the total distance that it travels as it goes round one cycle of the circle, as it were? Go round the circle once, the distance travelled will be 2 pi r. It's simply the circumference of the circle. And let's say that it does that journey in t seconds. Then the velocity v will equal the distance divided by the time, 2 pi r divided by t, and that will be measured in meters per second. But there's another way of measuring speed when you talk about moving in a circle, and that is the angular sweep. In other words, if the object starts here, this is the centre of the circle, there's the object, and if it moves round to here, it will have swept out an angle theta. And we normally regard a full circle as being 360 degrees. But we're going to work with a new unit called radians. The definition of a radian is that you take the arc length of the circle, which we'll call x, and divide it by the radius of the circle, r, and that is theta in radians. So theta is x divided by r, expressed in radians. So how many radians are there in a full circle? Well, a full circle, of course, is 360 degrees. We know that. The definition of a radian is the distance divided by the radius. Well, if you do a full circle, the distance will be 2 pi r. So that is kind of x for a full circle. Divided by r, because the way you get the angle is, the angle in radians is x divided by r. So that's, x will now be the full circle, 2 pi r, divided by r is 2 pi. So there are 2 pi radians in a full circle. So 2 pi equals 360 degrees. They're the same thing. Now we come to the subject of what's called angular speed, which we give the omega. And omega, the speed, is the change in the angle with respect to time. It's how fast the angle changes. So that will be the radians per second, which will be 2 pi divided by t. What we're saying is that that when the ball goes round a full circle, it sweeps out 2 pi radians, and it does that in t seconds. So the angular velocity will be the number of radians, 2 pi, divided by the time taken to do that full circle, t. So omega is 2 pi over t radians per second. Now I want you to notice the difference between this formula, omega is 2 pi over t, and the one that we worked out before, which was that v is 2 pi r over t. So v is 2 pi r over t, omega is 2 pi over t. That tells you that v equals omega r, because if you multiply both sides here by r, you get omega r is 2 pi r over t, but 2 pi r over t is v. So v is omega r. So that's a relationship between v, which is the orbital velocity, and that relates it to omega, which is the angular speed, multiplied by the radius r. Now we come to the concept of frequency, which we denote with the letter F. Frequency is the number of cycles per second, the number of times that the ball does a full revolution of the circle per second. Well, we know what the angular velocity is. Omega is the number of radians per second. So if omega is the number of radians per second, and 2 pi is the number of radians per cycle, omega the number of radians per second, 2 pi the number of radians per cycle, then F is simply going to be equal to omega over 2 pi. Because omega is the number of radians, but there are 2 pi radians in a cycle, so there are omega over 2 pi cycles per second. And thus you can write that omega equals 2 pi f. So that's the relationship between the frequency and the angular speed. Omega is 2 pi f. Another concept that we'll need to learn is the period t. The period is the amount of time it takes to do one cycle. Well, let's just think about it. Suppose the frequency is 10 cycles per second. That means it goes round the loop completely 10 times in 1 second. How long does it take to do one cycle? The answer is 1/10 of a second, because if it's doing 10 cycles in 1 second, every cycle takes 1/10 of a second. If it does 5 cycles per second, then it will take 1/5 of a second, 1 divided by 5. In other words, the time taken to do one cycle is always 1 divided by the frequency. So that tells you how you can get the period from the frequency. It's 1 over the frequency. So if omega is 2 pi f, it's also 2 pi, f is 1 over t, so it's 2 pi over t. Now we're going to consider the acceleration that we spoke about before, the centripetal acceleration. So let's consider this ball going round in a circle, and it's got an orbital speed of v. And this is the radius, and we'll call the radius r. Now after a short distance, it will have swept out an angle, and I'm going to call that angle d theta. And I call it d theta because I want to give the impression that it's a very small angle. I have in fact drawn it as quite a large angle, because otherwise you wouldn't be able to see it, it would be too confusing. But think of it as a very small angle. It has travelled a very small distance. The arc distance that it has travelled we're going to call dx, to indicate that it's a small distance, and we're going to say that it travels that in a time dt. So what we're saying is that the ball travels a small distance dx around the circumference, sweeping out an angle d theta, and it does that in time dt. And when it gets to here, of course its speed is still v, because it doesn't change its speed, but the speed is now in a different direction. And if the direction of the speed changes, then it has been subjected to an acceleration, and that's what we're trying to find out. Now, there are several things we can say. Firstly, we can work out that this angle in radians, which is d theta, is equal to the arc length, which is dx, divided by the radius, which is r. So that gives us one equation. D theta is dx by dr. That's just by definition of the radians. The second thing we can say is that the velocity is equal to the distance divided by the time. Well, it travels a distance dx in time dt. So the velocity is dx by dt. And that gives us a second equation. Now we need to know how the velocity changes, because acceleration is the rate of change of velocity. So we need to know what the change in velocity is. We know what the time is, that's dt. So if we can find the change in velocity and divide it by dt, that will give us the rate of change of velocity, and that's the acceleration. How are we going to do that? Well, we do that by looking, if you want to look at the difference between two vectors, you use the principle of putting them tail to tail. So here is the vector v at this point, here is the vector v at this point. We redraw those, but tail to tail. So here's the vector v, that's that one. And here is the second vector v, that's this one. And what we know is that they both are of the same length, because the speed doesn't change, only the direction changes. And we know, this is vector analysis, that the difference, dv, is represented by that line there. How are we going to calculate what dv is? Well, since these two vectors are the same length, they can behave like the radius of a circle. So we can in fact construct this as a circle where we have v and v, they're going to be the same length. This angle, incidentally, is d theta, the same as this angle here. You can show that just by geometry. And what we want to know is the straight line dv. And what we can say, of course, is that the arc length, which I'll call dy, the arc length of the circle, which is not the same as the straight line is absolutely straight, the circle is curved. The curved part, as it were, the arc of the circle, divided by the radius, is the angle. So d theta is equal to dy by v. That's the definition, show that again. That's the definition of a radian. The angle is the arc length divided by the radius, which in this case is v, so dy by dv. But here is where the trick comes. If d theta is very small, and I told you that it was, then the arc length effectively becomes the straight line length. And so we can say, provided d theta is small, we can say that that is equal to dv by v, because when d theta is very small, the arc length becomes a straight line when d theta is very small. And that gives us our third equation. So let's just remind ourselves, we've got d theta is dx over r, v is dx over dt, and d theta is dv by v. From this equation we can say that dx is r d theta. dx equals r d theta. But from this equation we can say that dx is v dt. So dx equals v dt. But d theta from this equation is dv over v. So we can rewrite this equation here as dx equals r. Now d theta we're going to put dv over v equals v dt. And now if we rearrange just this section here, bring the v up here to make that v squared, bring the dt down here, we get r dv by dt equals v squared. Or if you like, dv by dt equals v squared over r. But dv by dt, the rate of change of velocity, is acceleration. And that's the centripetal acceleration we were trying to find. So the centripetal acceleration is v squared over r, the orbital velocity divided by the radius. We've also learned that v equals omega r. V equals omega r. So if we substitute v in here, that becomes omega squared r squared divided by r is omega squared r. So centripetal acceleration can be written either as v squared over r or omega squared times r. So it's the orbital speed squared divided by the radius, or the angular speed squared multiplied by the radius. And then since we know that force is mass times acceleration, that's Newton's second law, the centripetal force can either be written as m times a, where a is v squared over r, or it can be written in this form as m times omega squared times r. Choice is yours. That's the centripetal force. I now want to take what we've learnt so far and apply it to some of the questions of the kind that you might get in an A-level exam. First, the fairground loop-the-loop. This is a ride which starts with a car up at a height. The car will start at 0 speed, but will then fall down the incline, come along here, loop the loop, and go round. And the question is that if this height above the ground is h, and the radius of the loop is a, what is the relationship of h to a to ensure that when the car goes round the loop it doesn't fall off? That's the question. How do you design it so that the car will have enough speed to stay on the loop as it goes right the way round and the passengers are upside down when they get to this point here? Well, what we can say, at point A, when the car is at the top of the loop ride, it has no velocity, but it will have potential energy. And the potential energy is given by mgh, where h is the height above ground. When it gets to the bottom of the loop ride, it will be travelling at velocity v. It won't have any potential energy because that's all been changed. So it will now have a kinetic energy of a half mv squared. We've learnt all this in the video on classical mechanics. When it gets to the top of the loop, it will now be travelling in this direction, and let's give it a speed u. So now that energy, that half mv squared, will have been converted into potential energy, which is mg2a, because the height above ground is twice the radius. So mg2a plus the kinetic energy, which will be a half mu squared. M, of course, in all of this is the mass of the car that is coming down the loop. So we know that mgh, the potential energy at this point here, is converted into part potential energy, mg2a, plus kinetic energy, half mu squared. But we've also learned that if this is going to go round the loop without falling off, it needs a certain centripetal acceleration. In fact, it needs a centripetal force. And that force is equal to, well, we sorted it was mv squared over r. Well, m is the mass of the car, the speed is u, so it's mu squared divided by r. Well, r in this case is a. So the force is mu squared over a. But how is that being provided? That's being provided by the gravitational force acting on the car, which is mg. The m's cancel out, and now we can see that u squared equals ga, simply by taking a up to the other side. U squared equals ga. So now we can substitute that u squared into this formula here. And that will give us that mgh equals mg2a plus a half m, and instead of u squared, I'm going to put ga. Now you'll notice that mg cancels throughout. And that leaves us with H equals 2A plus a half A, which is 2.5A. And that's the solution. What that means is that when you design your loop-the-loop, you must make sure that the height from which the car is going to fall is at least 2.5 times as big as the radius, not the total height, but the radius. Otherwise, the car will fall off when it gets to the top of loop-the-loop. In fact, 2.5A is the minimum you have to have. If you have it at that point, the car will only just stay on the track. So if you were designing it, you obviously would want to make it a little bit more secure, so you'd make sure that H was at least 3 times the radius of the loop to be absolutely certain that it was going to work. So that's the first example. The next question is, suppose you have a bucket of water and you want to swing it, this is your arm, around and over your head. The question is, what is the frequency, that is, how many times per second do you have to swing that bucket in order that the water doesn't fall on your head? So you're swinging a bucket of water over your head so that at the point that it's over your head, the bucket is actually upside down and the water in it is therefore available to fall on your head. But we want it to be in a position that it doesn't fall in your head, it stays in the bucket. What is the frequency with which you have to swing the bucket? We're going to assume that the radius, in other words, the length of your arm plus the bucket, is about 1 metre. And we're going to say that G is 9.81 metres per second squared. Now, we've already shown on the previous page that the centripetal acceleration is equal to omega squared r. And omega, you'll remember, is equal to 2 pi f. So that will give us the frequency. So omega squared is a over r. A is the gravitational acceleration. That's what's actually acting here. And that's 9.81. R is the radius of the circle. Well, we've said that the length of your arm plus the bucket is approximately 1, I should have said that's not m, 1 metre. So it's 9.81 divided by 1, and that's omega squared. So omega is going to be the square root of 9.81. Well, let's call that 3.1. And then we know that omega is 2 pi f. So f is going to be omega over 2 pi, which is 3.1 divided by, that's 3.1 divided by 2 pi. Pi is about 3. So 2 pi is 6. So the frequency is about 0.5. In other words, you have to do 0.5 cycles per second, or if you like, 1 cycle every 2 seconds. So, provided you swing the bucket of water over your head more frequently, in other words, you do the full cycle at least once every 2 seconds, the water will not fall on your head. But if you go slower than once every 2 seconds, then expect to be drenched. And the final example I'm going to do today is to try and find the speed with which the Earth travels around the Sun. Here's the Sun, here's the Earth. The Earth has mass little m, the Sun has mass capital M, and we want to find, as it were, the orbital speed v with which the Earth travels around the Sun. We're going to assume that the Earth travels in a circle. As I said before, it's actually an ellipse, but it's nearly a circle, so we can make this an approximation. Now, we learnt in the videos on gravitation Newton's formula that says that wherever you have two bodies, there will be a force, a gravitational force acting on them, which will be equal to a gravitational constant, capital G, times the mass of one body, in this case the Sun, times the mass of the other body, in this case the Earth, divided by r squared, where r squared is the distance between the centres of the two bodies. But we also know that that force is the centripetal force. That is what is providing the force that is keeping the Earth going round the Sun. And the centripetal force, we said, was mv squared over r. So the force, which is the gravitational force of gmm over r squared, is providing the centripetal force mv squared over r that keeps the Earth going round the Sun. Now you'll notice that the small m, the mass of the Earth, actually cancels out. And if you rearrange this equation here, you will get that v squared equals g capital M over r. And v, of course, is the orbital speed, the speed we're trying to calculate. So all we now have to do is to plug in the values of these three factors here. So we get that v squared is equal to g. Well, g is 6.6 times 10 to the minus 11, times the mass of the Sun. Well, the mass of the Sun is approximately 2 times 10 to the 30 kilograms. And divide that by the radius, that is the distance of the Earth from the Sun, which is about 150 million kilometres. So that's 150 times 10 to the 9 metres. Well, we don't want to be too precise about this, so let's say that 6.6 times 2 goes into 150 10 times. So now we've got 10 to the minus 11 times 10 to the 30, that's 10 to the 19, divided by 10 to the 10, that becomes 10 to the 9. Or if you like, to ease my calculation, 10 times 10 to the 8th, that's the same thing. And that's v squared, so we have to take the square root of that. Well, the square root of 10 is about 3, and the square root of 10 to the 8th is 10 to the 4th. So that gives us 30,000 metres per second, or if you prefer, 30 kilometres per second, which very roughly equates to about 20 miles. That's miles, not metres. 20 miles per second. So the Earth is going round the Sun constantly at a speed of approximately 20 miles per second, or 30 kilometres per second, and that's pretty fast.